Alrighty, let's look at this thing called the convolution. And it's usually with a star. So if I have two functions, f and g, you might see f star g of t like that. And that definition is the integral from 0 to t of f of t minus tau, g of t tau, d tau. So tau is the variable here of integration. T acts like a constant. What's nifty is that through integration properties, one can show that this could have just been f of t and g of t minus tau, like that, d tau. Okay, so we have that f star g is the same thing as g star f. That's always nice. You can distribute, again, because of properties of integration. We have f star g plus h is equal to f star g plus f, that's a plus, f star h. So that's neat. It looks a lot like multiplication that way. F star g star h, well, we could do this with the f star g first, so do that integral first, and then do the integral involving h. So all that stuff looks like multiplication. If we take 0, the 0 function, star f, that's the same thing as f star 0, and you get 0 out of that, the 0 function. However, big exclamation points here. It is not the case that f star 1 is equal to f. So we'll put a not equal sign. So it doesn't quite work the way one would hope, but it's nice. And the reason we do this or point this out in this class, this convolution, and I think everybody should see the convolution. We're not going to really do much with it, but the big deal is that if I take the Laplace transform of a convolution, so we take that Laplace transform, what we get is the product of the two separate Laplace transforms. And so where that comes in handy is, of course, in inverse Laplace transforms. So, you know, suppose I do all this stuff and I get that x of s, so this is an uppercase s, happens to, uppercase x, so happens to be a product like that we recognize, okay? We know how to undo that product, say. As in, you know, I see that f and g, big F and big G are these particular functions. I go, oh, I know those Laplace transforms. I can do an inverse Laplace transform. Well, then we know that x of t is equal to the integral from 0 to t. And again, it's our choice here because the products and so forth are commutative, but we could write this as f of t minus tau, g of t g of tau d tau. Now, whether we can do that integral or not, that's a different story, but we have succeeded in finding our x of t if we got to that stage, if we were able to get to that stage. And so that's the point, is just that this ends up being a very handy theorem. Now, what I want to do is look at a special case of something we could have done with partial fractions. So, suppose we have this situation where I know that my big X, I do this and I get 5 over s minus 2 s plus 3. Well, see, what I recognize is that, I can think of this as 5, that's just the constant, and then times 1 over s minus 2 and times 1 over s plus 3. We know how to do this. We would do partial fractions to do this, but with this convolution theorem, it says, well, since I know that this 1 over s minus 2 ends up going to e to the 2t, and I know that this 1 over s plus 3 ends up going to e to the minus 3t, like that, then what I can tell you right off is that x of t is equal to 5, because we do still have that constant, and then the integral from 0 to t of, I'll do the e to the 2t first, I guess, e to the 2 times t minus tau, in parentheses like that, e to the minus 3 tau d tau. So there's our answer. Now, in this particular case, I can do this integral. This is 5, integral from 0 to t, e to the 2t, e to the minus 2 tau, like that, e to the minus 3 tau d tau. Now that e to the 2t, that's just a constant in terms of tau, so I can make this 5 e to the 2t, and then integral 0 to t of e to the minus 5 tau, using my rules of exponents. So I have that, and so that's 5 e to the 2t, and integrate this, I'll get a negative 1 over 5 e to the minus 5 tau, like that, and that goes from 0 to t, and so that's equal to negative 1, I guess, because I have 5 over negative 5, so I get a negative e to the 2t times, and I evaluate this, I'll get e to the negative 5t, and minus e to the 0, or 1. And so that's equal to, well, using my rules of exponents and so forth. Now, here's this negative, so it's going to turn these two things around. So I'll do e to the 2t times 1, and two negatives make a positive, e to the 2t, and then minus e to the minus 3t. So that's my answer after doing that integral. Now, partial fractions, that was our other way to do this. And what you can pretty quickly show, oops, minus 2 s plus 3, so we have that, is that the partial fraction answer to this thing is 1 over s minus 2 minus 1 over s plus 3. So you know, if I multiply top and bottom of the first one by s plus 3, I'll get an s plus 3 here, and I'll get an s minus 2 here. Well, s minus s is 0, and then I had a 3 here and a minus 2 there. That's 5, so that works. And so now I know that this was my big X, and I do my inverse Laplace transform, x of t, and that first one we already know is e to the 2t, and then the minus e to the negative 3t for that inverse Laplace transform. And so you see we get those same answers, and so that integral, that 5 times that convolution integral, turns out to be equivalent to this answer. And so if you got stuck with a product that you couldn't undo, so here, you know, this is great. I could use partial fractions, but I didn't have to. And, you know, and if I couldn't, you know, if I never knew anything about partial fractions, or that nice theorem didn't exist, well, I still have a way to undo that Laplace transform. And that's really the big idea of these convolutions in the context of differential equations. Okay, so that's the idea here, and we'll stop this video at this point then.